Okay, this next section is called linear transformations and linear combinations. Now recall the definition of linear transformation. Linear transformation satisfies this: t of x plus y is equal to t of x plus t of y. That's one thing. And t of alpha x is equal to alpha t of x. Now these are both special cases of linear combinations. This is the linear combination of x and y formed by the sum. This is a linear combination of the vector x formed by the scalar multiple. All right. So these are special cases. In fact, the linear transformation of a linear combination is a linear combination. And that's true for a general linear combination, not just these two special ones. So that's the essence of this theorem here. Just look at the statement. If you take t of a linear combination of vectors, then you get a linear combination with the same constants, but the vectors involved are the images or results of the vectors, the original vectors, after t has been applied. So you can say in a sense that linear transformation preserves linear combination. And this proof shouldn't be surprising. You just repeatedly apply the definitions. You repeatedly apply these two rules to decompose an arbitrary linear combination into the t of an arbitrary linear combination into a linear combination. Okay, so let's use this. We know that when we have a basis, we can write any vector as a linear combination of basis vectors. So what does this mean? If we know what the linear transformation does to the basis, we can form arbitrary linear combination of the basis vectors and get any vector we want. So that means all we need to do is know what the linear transformation does to the basis vectors, and that gives us the linear transformation on any old vector we want. Here's the formal statement. Suppose U is a vector space that has a basis u1 up to un, and the vector space V contains vectors v1 through vn. Then there's a unique linear transformation from u to v such that t of ui is equal to vi. In other words, if I define the linear transformation on basis vectors, then the linear transformation is defined for any vector. All right, so to prove this, basically we construct a linear transformation based on the prescription that t of each basis vector is the corresponding given vector in the codomain. All right, suppose W is an arbitrary element of the domain. Then there are unique, here's this important thing, there are unique scalars that make W be a linear combination of basis vectors. Okay? Then we can define a function t on this vector W as alpha 1 times v1 plus alpha 2 times v2 dot 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 alpha n times vn. Okay. All right, so we've defined a function, and actually it's well defined because for any vector W, I can find unique scalars A, and once I've decomposed W in this unique way, I have a unique way of specifying t of W. Then you can go ahead and show that this function is in fact linear. T of W plus x equals t of W plus t of x. You write W as a combination of basis vectors. You write x as a combination of basis vectors. You use your linear properties to show that this, or you use your properties of basis vectors and properties of addition of vectors in the vector space to show that we get the linearity of addition, and similarly for linearity of scalar multiplication. Okay, so that shows that we have a linear transformation defined when we know what the linear transformation does to the basis vectors. So the question is T unique? Is there another possible linear transformation that takes the ui's to the vi's? Well, suppose there is a second one. The upshot is that I can define T of W as a linear combination of T applied to the UIs. But if T and S agree on the basis vectors, then I can reconstruct T of the original vector and S of the original vector from the action of T and S on the basis vectors. If they agree on the basis vectors, they have to agree on any vector. Okay, here's a nice analogy that he makes here, that 2 points determine a line and 3 points determine a parabola. Here we're saying that the linear transformation on a basis of the vector space determines uniquely the linear transformation for the entire vector space. All right. So here's an example. Suppose I define linear transformation on the standard basis for C3 in this way. T of 1, 0, 0 is 2, 1. T of 0, 1, 0 is this vector. T of 0, 0, 1 is this vector. Now we know this is a standard basis. We've defined T on each basis vector. That means that T should be defined for any vector in C3. How do we get T for any vector in C3? Well, if I take an arbitrary vector, for instance this vector, I can write it as a linear combination of basis vectors. And then if I want to take T of that vector W, I'm just going to take the same linear combination of the image vectors. Right? This is the image vector here. This is the image vector here. This is the image vector here. And then add them all together, I get my result. Here's another example, same thing. Okay. Now that was an easy example where he shows an easy basis for the domain, but in fact we can choose any basis for the domain. Here's a basis for C3, these three vectors. You have to verify that these three vectors are in fact linearly independent, or the columns of a non-singular matrix. All right? And this fulfills our condition. We've defined the linear transformation R on a basis for C3, which means that R is defined for any vector in C3. For example, let's consider this one. It turns out, and we've seen how to do this, that you can write this vector as a linear combination of these three basis vectors. So you can remember how to do that from your past experience. Here's the expression of the vector v as a linear combination of these three vectors. To get the result, the linear transformation applied to this vector, all I have to do is take the same linear combination, applied to the results of each individual basis vector. I know that 1, 2, 1 maps to phi minus 1, so that's what I put in here. I know that minus 1, 5, 1 maps to 0, 4, so that's why the 0, 4 is here. And I know that 3, 1, 4 maps to 2, 3, that's up here. So that gives me the arbitrary result. All right, now we've been talking about vectors C3, etc. But let's now look at a more complicated vector space. Let's look at a linear transformation on the space of polynomials. Actually, we had this example of a linear transformation from the space of polynomials to the set of matrices. And in fact, we're not just going to do space of polynomials, we're going to do a subspace. This set W is a subspace of the polynomials of degree 3. It's the subspace of polynomials that are 0 when x equals 1 and when x equals 3. It turns out that these two polynomials form a basis of this subspace, and we can consider a linear transformation from this subspace to the 2 by 2 matrices. And we can define it by defining the linear transformation on the basis vector. So linear transformation on this basis vector is this matrix. Linear transformation on this basis vector is this matrix. Now, as we said before, to get the linear transformation applied to an arbitrary polynomial in P3, we just need to express that polynomial as a linear combination of these two basis vectors, and boom, we're done, because we know what that linear transformation does to the first basis vector and what it does to the second basis vector. Here's a particular example. Here's a polynomial q. You can verify that q of 1 is equal to 0, and also that q of 3 is equal to 0, so q is in the space P3. I'm sorry, q is in the space, is in the set W. Okay, so let's let's express this in terms of the two basis vectors. My two basis vectors are here. You can show, using methods that we've used before, that this q, this polynomial q, is the following linear combination of the two basis vectors. Now, we know what s does to this basis vector, that's up here. And we know what s does to this basis vector, that's up here. So that tells us what s does to q. It's minus 5 times this result plus 2 times this result. It gives us an easy expression for the result. Okay. All right, this is a good place to stop, and we'll pick up with the next video.